All right, in this video we're going to talk about molecular formulas and how they relate to stoichiometry and to doing calculations relating to mass or atoms or moles in regarding to molecular formulas of compounds, of molecules, of multi-atom formulas here. So we got to remember that in this molecular formula, I give an example, C4H10O, that it's a mole ratio that's there, but it's maybe best understood from the fact that in one molecule I have 4 carbon atoms, 10 hydrogen atoms, and 1 oxygen atom. So I can set up a formula or an equivalent statement, a conversion factor that says for every 1 molecule of C4H10O I have 4 atoms of carbon. And if we recall Avogadro's number, then I can convert the moles or the molecules of C4H10O into a mole using Avogadro's number. I can do the same thing for the atoms of carbon, but this time I would need to have the atom part of Avogadro's number in the denominator. And so doing, all of the molecules cancel out the terms there, the atom terms cancel out, and I'm now left with moles of carbon over moles of C4H10O. So that atom to molecule ratio is the same as the mole to mole ratio of the molecule to one of the individual components, like the carbon atom. I could have used 10 moles of hydrogen as my equivalent, part of my equivalent statement or my conversion factor, or I could have used oxygen. Remember, if there's no subscript, it's not 0, because then why would we write it? It means that there's a 1 there. And then also, if I want to do individual ratios for whatever the problem may be asking me, I can just do 1 mole of oxygen to 4 moles of carbon, or 1 mole of oxygen to 10 moles of hydrogen, 4 moles of carbon to 10 moles of hydrogen, and then I can flip around and use them as I want. So these mole ratios are always there. The problem doesn't need to state, well, student, you need to go look at the molecular formula and figure out what the mole ratios are. It's always assumed that you can always do that, so you're not going to be told. These are tools now for you to use. Now, and then also, as I mentioned many times, these are equivalent statements. So you flip them as you need them to get the units to work out. In general chemistry and in a lot of problems in life, it's all about the units and getting them to work out. Let's take a look at a problem that puts this into practice. How many grams of boron are present in 4.11 moles of boron trichloride? So something we may need in some of our problems here dealing with boron trichloride is the molar mass of the entire compound. Well, if I go to the periodic table, I can look up boron and chlorine, and recalling the formula, there's 1 boron and 3 chlorines, and I can multiply the 10.811 grams per mole times 1, times it by B there, but it's just 1 boron, and then there's 3 chlorines, and so that we can add all that mass up. And so boron trichloride as a compound weighs 117.17 grams per mole. Now let's put this into practice in the next few problems here. Let's go back to that problem, and let's see how many grams of boron in 4.11 moles of boron trichloride. Well, I'd start with what they're given, and I think about how to get to where the answer is asking me. So I can go from moles of boron trichloride into moles of boron using the molecular formula. And once I'm into, so the moles of boron trichloride would cancel out, and I'm going to have moles of boron. Well, in 1 mole of boron now, there's 10.811 grams. Now I can multiply everything along the numerator, 4.11 times 1 times 10.811, and get 44.4 grams. Everything's divided by 1 at that point, and my units cancel out, and I get to the desired answer. Let's look at problem 2. How many moles of chlorine are present in 4.15 grams of boron trichloride? Now I have 4.15 grams of boron trichloride, so I should start there, and I can convert to moles of boron trichloride. It's asking for how many moles of chlorine. Well, I need to dig into the formula again once I have the moles of the compound, and I can use the molecular formula to go from moles of boron trichloride to moles of chlorine. So you may come up with another way of solving this, but this is the most straightforward way using the units. And once again, if I divide by 2 sets of units, they essentially cancel out. They turn into the number 1, and we can remove those units. So this is what you're going to be expected to do now, and to be able to use the molar formula as a molar ratio between the elements and between the molecule itself.